Let's get started with the morning session. So the first speaker this morning is Evelyn Legendre from Toulouse, and she's going to talk about extremal Sasaki structures and weighted cscK metrics. Go ahead.
Hi everyone. So I hope you hear me. Okay, so thanks a lot for the invitation. I think it's a very nice conference. It's hard to follow a conference when you're at home and you have all the things to do, teaching and stuff and parenting. But it's nice that the talks are recorded, so I watch it on the morning or something like that. So nice talks, guys. And I really wish I could be in Montreal with you, of course. Okay, so I will talk about a joint work with V.Apostolov and D.Calderbank on extremal Sasaki structure and weighted cscK metric. Okay, so maybe before going in the details, I can just say briefly what I mean and what it will be about. So by extremal Sasaki structure, what I mean is what was called canonical Sasaki metric by Boyer, introduced and called canonical Sasaki metric by Boyer, Galaxy, and Simanka. Okay, so these are Calabi type extremal metric, let's say a Sasaki version of Calabi extremal metric, but a Sasaki version. And here, what I mean by weighted cscK metric, I could have also called it weighted extremal metric. I mean some very particular case of a more general notion introduced in a very big generality by Lahdili in his PhD thesis. And so maybe I can say now that the work a big chunk of my talk will be explaining a result which is not due to me, but to my collaborators, V.Apostolov and D.Calderbank, who gave a very nice formula relating these extremal Sasaki extremal equation, let's say, as this particular case of Lahdili extremal metric. And then our work was essentially, well, not essentially, but was extending in some sense this notion to be able to work within a class, varying the matrix structure, but keeping some class fixed. So maybe to give maybe more details. So I don't know why my tablet is not working just now. Sorry for this. Maybe this will work. I don't know. Oh yeah. Okay. Okay, so maybe I can recall, although it's very well known. Maybe I can just recall the Calabi problem on compact manifolds. So I assume that you have a Kähler manifold, and actually which is compact, and we consider the Kähler class. Well, I'm just recalling the Calabi problem, so most people know very well what it is. And then the question of Calabi is, does there exist an extremal metric, so a special metric, an extremal metric in the class? Okay. With respect to the complex structure, which is fixed and will be fixed all the talk, and then I don't know what to do that. anyway. So what do you mean by extremal metric is if you look at the Hamiltonian vector field of the scalar curvature of the metric, so I call omega, little omega in the metric, then you ask it to be a killing vector field, okay, or a real holomorphic vector field with what is given, which is equivalently, so let's say real holomorphic, which means that that this vector field xcal J is equal to 0. So it produces isometries. The flow is isometries, or I'll leave the complex structure fixed. Okay, and so this is a Kähler problem, and Boyer and Galaxy and Simanka have given one not necessarily generalization, but a Sasakian version of this problem. And what is nice that so the work of Apostolov and D.Calderbank that I want to talk about is that they showed that these extremal metrics are essentially a particular case of Lahdili cscK metric. And so what's important in the Kähler problem is that you have to allow moving in the class. So omega is a class which is 1,1 with respect to the complex structure. And so typically when you pick a Kähler metric in the class, it won't be extremal. And so you look within the class, and so you need to allow some variation for the problem to be solvable. So and this is what we did actually with Vestislav and David, was to starting with to try to find some kind of to extend their results to look within the class. Okay, so what I will do first, I will talk about just a Sasaki geometry, let's say revisited, just introduce some notations, and then I will explain the formula of Vestislav and David, Apostolov Kählerbank, and then I will explain what I meant by varying the metric within the class, and also I will say what I mean by downstairs, and with that we actually we had application in the study of the Mabuchi functional, the weighted version or the Sasaki version of the Mabuchi functional, and that allowed us to improve a result of Collins and Sekaidi. So maybe I would probably don't have the time to get there, so maybe it's better I'm saying already what's the main application. So so we used our result to prove that whenever there exists an extremal Sasaki metric, so maybe I can say that this way. So like, I'm sorry, whenever there exists, I don't know what's happened with my tablet right now, sorry for this. So whenever there exists an extremal Sasaki metric, whenever there exists a Sasaki metric, then the Mabuchi functional, that I would call, that is with respect to some vector field psi that I will talk about later, is as some properness, satisfies proper in some sense with respect to some kind of torus that I will define later. Okay, so there was a similar result by Wei Hong He, and actually proved that it was equivalent, but that was not exactly the same kind of properness he used, and so the result is slightly different. I hope I will get there. And another application was to improve a result from Collins and Sekaidi spéciales, from K-stability, K-semistability, sorry, to K-stability. So this is very in some specific case that I will define later, like very something specific, and some. So like here we ask for the total space of the test configuration to be smooth, for example, which is well, which is a strong this is a strong hypothesis, and so this is not completely general, but still I think it's interesting. And this is really using Lahdili's result on weighted cscK metric. Okay, so but first let me begin by Sasaki Geometry. Well, just to set up some notation, and in case some people in the audience don't know about all this. So N is a compact connected manifold, what would be the Sasaki manifold, bearing the manifold bearing the Sasaki structure. So D is a contact distribution. So it means that it's a codimension 1 subbundle, if you want. And D is a contact form. Okay, so here typically D will be the contact distribution of N. So it means that D is the kernel of eta, and D eta is non-degenerated on D, and typically I will also pick a CR structure. So it means that J will be an endomorphism of D that squares to minus the identity. And we also assume that satisfies some integrability condition that I will not make precise, but typically if N is given as an real hypersurface in a complex manifold, then you can define D as well, G. I'm sorry, J as the restriction of the complex structure, and D is just where it ends with that, and D is well, is a subbundle on which J act. And then Xi will be what we will call the Sasaki Reeb vector field. And so Xi is just a vector field over N. And actually it is transverse to the distribution. So it means that it's never zero. And it's also never tangent to D. Okay, so it might look complicated this way, but the prototypical example is has been well. I know that some people have talked about this kind of idea this week in few times. So when you have a compact complex manifold and you have a Kähler class, which is integral in that sense, so you have S1 bundle over M, your compact complex manifold, and you can pick a connection 1 form, which is whose differential is the pullback of omega by the bundle map, and then this gives a contact Sasaki manifold with D, the contact distribution being the kernel of the connection 1 form, and then you can really identify D to the tangent space of the compact complex manifold you started with. And actually you can also pull back the complex structure, and so you get a CR structure satisfying all this. Okay, so this is an example of a regular Sasaki manifold in the sense that here the action is free. The S1 action is free. Okay, so and so it induces a Reeb vector field. So our vector field, let's say just for now a vector field, which will be the Reeb vector field, and then we will call a regular just because it's free. Regular Reeb or Sasaki Reeb vector field. Okay, so so in general, so when n d j psi is just a Sasaki manifold as before, then psi is so if psi generates not a free but a locally free S1 action. Actually, as soon as it induces a S1 action, it's going to be locally free because the Reeb vector field is never zero. Then we say that it's quasi-regular. And if not, we say that it's irregular. Okay. And in that case, so in the quasi-regular case, so when n d j psi is a quasi-regular Sasaki manifold, then in this case we call m omega j the Sasaki Reeb quotients. Orbifold quotient. So maybe it's not so clear here, but since I'm going to use it all the time, maybe I can write it in blue. Is that if you have as soon as you have a contact distribution, so in particular a CR distribution fix, then a Reeb vector field or a Sasaki Reeb vector field determines and is determined by a contact form. Okay, so I could, so I can write a d j psi for a Sasaki manifold. And actually I can replace and the j is the same, but then I can pick the contact form and it determines the same one. So here, just to recall, so this one is a Reeb vector field, and eta is the contact form, and they are linked as follow: Lxi is equal to 1, and Lxi is equal to so eta is psi invariant. So this is the equation, making it unique together with this fact. Okay, so I will often just take one side or the other, and so here the Kähler form is determined all the time by this relation, and although it's not always quasi-regular, you can always think about it this way, as the differential of the contact form is locally a Kähler form on the local quotient. Okay. Okay, so this is just put some notation in the way we use it. Now we want to talk about scalar curvature. And so given a Sasaki manifold, the Sasaki matrix, so this is a Riemannian matrix, refers to this bilinear form. Actually, in what I will do, I will not use the Sasaki matrix itself. I'm using just the transverse structure. So really what happens on D, essentially, or on some quotient, local quotient. And then, so actually, I will not be interested in the whole scalar curvature of the matrix, which is this one actually, but the transverse scalar curvature, which happens to be just the Riemannian scalar curvature of G, but plus 2n. But this is an accident. This is not really interesting. It's really just because we are interested in this transversal scalar curvature. And the reason is, I'm just writing this curvature. And the reason is that this actually gives exactly the scalar curvature of the local quotient. Okay, so it means that when the associated Reeb vector field that I called Xi before and now is well, when it's quasi-regular, it can take the global quotient, and this scalar curvature will be actually the scalar curvature of the quotient, and this is the one I'm interested in. Okay. Maybe a better way to define this curvature is to consider the connection that is induced on the transversal. So the transversal Kähler structure, let's say, would refer to D with the complex structure on that bundle, and well, let's say D eta if you want. Okay, which gives a transversal Kähler structure. And from this, you can compute, well, you can define a connection very naturally, the Tanaka-Webster connection, which is just a connection for which all these objects will be invariant, and for which the torsion will satisfy something, some nice equation. And Liana David proved that the Levi-Civita connection of the local quotients, so the one we are interested in on the quotient, pulls back to the Tanaka connection of this transversal Kähler structure. And this was used by Apostolov and Calderbank to prove their result. Okay, so we are on a CR manifold of Sasaki type. So it means that there exists a contact form which is compatible with the CR structure here. And we are considering two Sasaki Reeb vector field that I will call Xi and Xi0. So they are CR vector fields. So in the sense that well, in the following sense, they leave G invariant, and they are also a contact vector field. Okay, so CR and a basic fact which is important is that the CR transformation lies inside a contact transformation. Okay, so it means that it's so these are the vector fields. Well, maybe not this way. So here, these are the vector field sending section of D to section of D, where S is a section of D. Okay. Okay, so the setting will be that I'm using two Sasaki Reeb vector field that are commuting. Okay, so you know what it means, commuting, I guess. And so what I mean by that is that they are both compatible with NDJ, so the CR structure, in the sense that NDJXI and NDJXI0 are both Sasaki manifold. So with respect to the same CR structure. Okay, so I will look at the associated contact form. So eta is the contact form of Xi, and eta 0, the contact form associated to Xi 0 with respect to D, of course. And because they are both Sasaki manifold, actually, it's not hard to prove that the two forms, eta 0 and eta, must be collinear. I mean, pointwise collinear. So it means that eta, oh, maybe I can write blue here. So it means that eta will be equal to eta 0, but divided by something positive, which will be just the value of Xi 0, the value of eta 0 on Xi. Okay, so eta 0 Xi will be positive. Okay. It's okay. We're not all lost. Okay. Okay, then the formula of Apostolov and Calderbank, which is, I think is very nice, is this one. Is that the transversal scalar curvature of this structure, of that structure, right, is actually a nice expression of the transversal scalar curvature of the other structure. Okay, so here I forgot to tell you what's f. So here f is just this function. Okay, and then well, it's a closed formula, which I think is could be very useful anyway. Okay, and now to explain how this this can be related to the weighted cscK metric, I will need to give you more details. Okay, and maybe I have to define extremal Sasaki metric at some point. So this is what I will do first. So a Sasaki structure. So here you see I'm choosing to write the contact form instead of the Reeb vector field. So a Sasaki structure is extremal in their sense. Actually, we called it canonical, but same. If there exists a CR vector field, such that the transversal scalar curvature is eta of that vector field. This is not the way they define it. They define the canonical extremal, well, the canonical Sasaki metric as a critical point of some functional involving the transversal scalar curvature, or just the scalar curvature of the metric. But actually, we can prove. We can check that this is equivalent to that, and to see this, maybe it's better to observe something. So just notes, a remark. Maybe the first remark I've already done it, but it's important, so I will repeat it. Is that the CR vector fields are included in the contact vector field. Okay, and the second one is that for all function h on the manifold n I'm working on, there exists a unique contact vector field xh such that eta xh is equal to H. Of course, this vector field, I define it depends on eta, right? Clearly. Okay. So maybe I can write eta here to be clear. Okay. And then with that, we can give a definition, the following. Maybe a first definition is that H, just a smooth function on N, is, well, let's say D, J eta killing potential if XH eta is lies in CR, so is a CR vector field. Okay. Then a Sasaki structure. So we get an alternative definition for extremal Sasaki structure. A Sasaki structure is extremal. So again, and D, J, let's say eta, is extremal if it's transversal scalar curvature is a killing potential, is a D, J eta killing potential. Okay. And so, yeah, maybe it's repetitive with what I wrote just here. Yeah, so it's maybe I can, but okay. So sorry for this. Maybe I can erase that then. Okay. So now to explain exactly what how to relate this to the weighted cscK setting of Lahdili, we need to get at some point to on some Kähler compact manifold, and also to pass from one polarization, one Reeb vector field to another one. Okay, so maybe a first observation I want to make is that, and for this I will maybe it's good to fix at some point some torus. Okay, so assume that you have a torus T, a torus compact. Okay, and you have two Sasaki Reeb vector field for a given contact structure in the Lie algebra of that torus. Okay, I'll just take that away to have more space. Okay, and then from this we can observe that if we have a function which is T invariant, okay, so it's going to be psi 0 and psi basic, is a D J psi killing potential if and only if H eta X, well, H, and then, so this is where X is CR, DJ, okay. And so in this case, because eta is eta 0 over some positive function, then you can write it this way. And so it implies that H time eta 0 applied to psi, so this thing is the function f, that we wrote before is a dj xi0 killing potential. Okay. So very good. So it means that we have a way to compare the killing potential from one Reeb polarization to the other. So and now we want to get to some Kähler manifold. And so we will assume typically that xi0 is quasi-regular. Okay. And so maybe just a second observation is that if xi0 is a quasi-regular, so it induces a S1 action, which is locally free. Okay, and then M is a quotient as an orbifold, and it comes with a Kähler structure and a complex structure. So very good, and then if H is a function on N, which is T invariant, actually it doesn't have to be that much T invariant, then is killing. So with the structure we have upstairs, then H is a pullback of a function, let's say H hat, where H hat is a function on M, which is T, T invariant by the induced action, so T quotiented by the S1 action, where an H actually is a killing potential with respect to the Kähler structure we have. Okay, now I can state what the results I wanted to talk about. First, from Apostolov and Calderbank, this is Lav and David, and so they have that if you have an extremal Sasaki structure commuting with a quasi-regular Sasaki structure, so in the sense that the Reeb vector field commutes, so it is extremal if and only if the regular Sasaki Reeb quotient is weighted extremal in the sense that that thing is a killing potential. Okay, so this formula is almost what we had before, but we have multiplied here F here and there. So here it's not, it's sorry, I have a mistake, I see. Here, there's no F. So this is almost what we had before. Okay, we just have to multiply all the formula by F because of the first observation. Okay, which was there. So you have to multiply to get potential to potential. And then this is the formula multiplied by F. Okay. Okay. And then actually to be able to say that it's a weighted CS as a type of weighted cscK metric, we need to introduce cscK metric in general that I know a weighted cscK metric in general that I don't want to do. But but I might be able to talk about that later. So maybe one thing before continuing to our result, just maybe now that I've introduced all this, I can talk a bit more about the picture. So the idea is that, so assume that both, like just to give an idea, like assume that both Reeb vector field xi0 and xi are quasi-regular. Okay, so in the setting you get two Kähler quotient, which is m, m, which is n quotiented by the action of xi0. First we had before, like omega 0, let's say, and some complex structure, and also another one, m, which is quotiented by the S1 action given by xi, so the other Reeb vector field that I now assume to be quasi-regular too, and also a metric. So their result says that that one is extremal. So this one is extremal if and only if. So if and only if here omega 0 is extremal, but with some weight, and the weight is completely determined by xi. So xi extremal. Okay. And this is reminiscent of Swan's twist, which was used by Swan to build to get from one hyper counterstructure to try to build another spatial structure on another manifold using a principal bundle, actually on which T2 act, and then you get one manifold. Let's say maybe I should not call, so M0 here and here M, so M0 and M. Okay, and this is a very natural idea, thinking about it, in the sense that if you have a spatial structure on one manifold, which is invariant by the group you get here quotiented by the S1 action, so here this is taking the quotient by some S1, then this should exist in some sense or in some, well, in some form to be found there. Okay. So yeah, so this idea is not, well, it is very natural in some sense, and but necessarily easy to work with. And so this is the result of Vesislav and David. And so what we worked on together, and we proved something, I hope I will have time to explain, is that so like in the original Calabi problem, we cannot expect the metric the metric we obtain just like that. We pick one metric, it's unlikely to be extremal. And to have a problem that makes sense, we need to take some variation into some class. And in the on the Kähler level, it means that we are trying to find an extremal metric within a class, within a given a Kähler class. In the Sasaki setting, we need to work on some kind of deformation, and we need to work on with transversal holomorphic structure that is fixed, and then vary the structure within this this transversal holomorphic structure. Okay. So this is my second section, and there's 15 minutes left. Very good. Okay, so what we do next is to try to explain at least where the result we have stand. So we have these are the ingredients I will use, and I already introduced. So I have a regular Sasaki manifold. Actually, for most of things that I will say, only quasi-regular is necessary. But well, you can think about regular, so everything is smooth. It's very easy to think about. And then you have a compact Kähler Sasaki Reeb quotient. And Xi is another Sasaki Reeb vector field on N. And we ask that, of course, that Xi and Xi0 commutes. Okay, so in particular, they both lie in a torus, in the Lie algebra of a torus that we call T. Okay. So with that, just let's introduce another notation again. So G Xi Xi will denote a transversal holomorphic structure. So it means that this is the local quotient. So it means that G Xi is a complex structure on the bundle, which is a quotient of the tangent space of N by the action of Xi. Okay, and then and a CR structure. So maybe a remark like a CR structure, as I had before, DJ induces a complex transversal holomorphic structure. Holomorphic structure. Well, actually, a CR structure compatible with Xi, a Reeb vector field, and this is a transversal holomorphic structure, J Xi Xi. Okay, and but actually, you might have many many CR structure that gives the same transversal holomorphic structure in the sense that well, when you look over the quotient, it gives the same thing. Okay, here it gives the same thing. Okay, so given that we define the Sasaki structure compatible with this holomorphic structure, so this is the Sasaki type CR structure compatible with that induce the same transversal structure. You can think about that as contact form, okay, which satisfy these conditions, so that the Reeb vector field will be given by Xi, and then for each of these CR structure, one red, for each of eta here, then actually the CR structure will be given by the kernel of eta. Okay, and then J will be the only complex structure, the only endomorphism which is mapped to J Xi here. Okay, so what did I want to say? Yeah, so maybe a small remark, like if Xi is quasi-regular, then with quotient and Xi, so working within a class when a transversal holomorphic structure fix is just working with the complex structure fix below. Okay, so J Xi is putting a complex structure on and Xi. Okay, and for each eta within the Sasaki class or the Sasaki structure on that holomorphic transversal holomorphic structure, actually it gives via its differential, it gives it corresponds to a Kähler structure within the same class, the same Kähler class. Okay. Okay, so actually maybe another way to say it is that eta, so if you have two, and this is true when even if it's not quasi-regular, so if you have two contact form compatible with the same transversal holomorphic structure, then one is the other plus d c phi. So here, what does that mean on the Sasaki manifold? Actually, you take the basic one form. So this is for the local quotient, and then you might have had to add a closed form. And so then the Calabi, well, the Sasaki version. So this was the remark, and then the Sasaki version of Calabi problem is just, does there exist an extremal metric, extremal Sasaki metric in SAS, sorry, not DG, but G, psi. Okay, so fixing, so in the original Calabi problem, you fix the Kähler class, and actually here you fix the Reeb vector field, and the holomorphic transversal scalar curvature. Actually, in the original Calabi problem, you fix the complex structure and the Kähler class. Here you fix the transversal holomorphic structure, which actually needs to be defined a Reeb vector field. Okay, so with that, to explain the rest, I still need to talk a little bit about the momentum maps. So when you have a Sasaki, when you have a Kähler manifold arising as the Sasaki Reeb quotient of a Sasaki manifold, which is then quasi-regular, then and so if you have a torus action on n, of course, the quotient by the S1 action also acts on the quotient. But what I want to say now is that in this setting, you have a natural momentum map on the quotient, but the image will not be in the dual of the Lie algebra of the quotient, but in the dual of the Lie algebra of the torus acting on n. Okay, so this is very well. This is like in the polarized case when you have an action on a line bundle, a linearized action that induce very naturally a momentum map. And here the momentum map is given as follows. It's just given by the contact form, right? So here the contact form is the one associated to psi. So here I assume that I have a CR structure fixed, and so the reason why I'm telling this, and I think it's important, and it's because via this observation or remark that you can see the Reeb vector field, or the Sasaki Reeb vector field, as as an element first in the Lie algebra, and so it's also a function on the moment polytope, which is naturally normalized in the setting. Okay, and this is not any kind of function. This is a positive function. So psi corresponds to a positive function on the normalized, more normalized polytope. For those of you who are aware of the work of Lahdili with weighted cscK metric, then that fits completely with the Lahdili's normalization. And actually, when you have two, if you take another one, well, let's say eta 0 and eta prime, both in the same Sasaki space, Sasakian structure with respect to psi0, let's say, then actually the momentum map will change. The map will change, but not the momentum polytope. Okay, because you will get exactly eta prime is equal to well, or maybe yes, it's gonna be eta 0 plus dc some function, which is going to be invariant, the basic part plus some closed form, but this closed form will be 0 on the torus, on the Lie algebra of the torus. So the momentum map will not change. And so even if you change the form, the moment polytope will not change. And so you can define an extremal Kähler metric, a weighted extremal Kähler metric in this very specific sense. So a very special case of the Lahdili's weighted extremal metric is a metric such that this function, the scalar, the weighted scalar function, is a omega killing potential. Okay. So omega here is in this class, and this function was defined just before, and f is given simply by the pullback. So as I said, so omega will change with the metric or will change with the structure, but psi will stay the same, and the image will be the same as a normalized omega momentum map in the sense of Lahdili, if you want. Okay, so with that, I will be able to say one result we have together with V.Apostolov and D.Calderbank. So if we have a compact quasi-regular Sasaki manifold with induced transversal holomorphic structure J xi0 and complex orbifold obtained as a quotient. So the Sasaki Reeb quotient and Kähler class. Then for any Sasaki Reeb vector field on xi on ndj commuting with xi0, there exists an extremal Sasaki structure compatible with the transversal holomorphic structure if and only if there exists a psi-weighted extremal metric in omega. Okay, so this says well, the addition that we have here compared to the Apostolov Kählerbank result is that we can allow variation within the Kähler class below or within the transversal the CR structure compatible with the transversal holomorphic structure. And so maybe in the 2 minutes I have left, to prove this, we needed to compare the compare this set of Sasakian structure compatible with transversal holomorphic structure with another, right? We needed to compare SAS J xi xi and SAS J xi0 xi0, and so this is the thing we needed to prove this result essentially, and we achieved that using polarized complex cone. So it's well known that Kähler cone, so in the sense of a variety, which has a cone structure and a Kähler structure, or a variety, I would say a manifold, a smooth manifold that has a Kähler matrix and a cone structure, are in one-to-one correspondence with Sasaki manifold, and so we use this correspondence to to do that. And instead of working with the metric on the Kähler cone, we work with the potentials. Okay, and so maybe I will pass this example. So there's a one-to-one correspondence is and the potential of the Kähler metric are completely determined by the level sets actually, and that was not well, this was probably known actually in some senses very simple. So so because the potential has to be invariant by some action, and so of course it's determined by its level set. So this is very just an obvious observation. And less obvious, there's this lemma by He and Son saying that when you have two commuting Sasaki Reeb vector field, then you can actually identify the complex cone as complex manifolds. And then from this, we build a bijection. When we build it, we just realized that there was this bijection between the sets of radial potentials, given just by the level sets must be the same. And well, this is the very simple observation, but this was very crucial to get our result. So thanks a lot for your attention. And sorry, it was, well, I prepared a few stuff, but it's, yeah, time flies. So
Thanks very much. Are there any questions in the audience?
Yes, I have a question. I just,
Yeah, go ahead.
Charles Boyer, very nice talk. So I was just thinking, when you use the Apostolov and Calderbank result, you're assuming that there exists a regular Reeb vector field, but there are of course many structures that don't have a regular Reeb vector. There are many Sasaki CR structures which don't have a regular Reeb vector field. The work with the Christina Tennyson-Friedman and I have done have looked at what we call S3 join constructions. And in those, you have what's called an almost regular Reeb vector field, which means that the weights are equal, but there are divisors where the ramification index on these divisors are the same. On the divisor, which is a zero section of a projective bundle, and the infinity section of a projective bundle. So there one might be able to generalize what you're doing. I was just wondering whether you have considered looked at that possibility.
Actually, there's, like, for example, in the result, which was just like the first proposition in the paper that I presented, it's really just need to be quasi-regular. So it's more general. But in the result, I didn't present because I had no time, and I took more time for doing nothing. Was indeed we need some regularity.
Yes.
And this is because essentially because we are relying on some result by Lahdili. And in this case, well, it's based on some work by Darvas and Rubinstein, and it's not so clear that in the orbifold case that it works. But to answer your question, we didn't try to apply it on.
So my guess would be that
case.
Yeah, my guess would be that one could generalize that. That's just a guess.
Yeah. So I
So-
guess that yeah, that probably well, it's probable. Yeah, I guess also that it's possible to generalize.
It's a very nice result as is.
Yeah. Okay. Thank you.
Hi, Evelyn. This is Claude.
Hi, Claude.
Is there any direct analog or a reinterpretation of the Calabi functional and Calabi's variational problem in this Sasaki context?
Yes, this is the way Charles Boyer, Galaxy, and Simenka have introduced extremal Sasaki matrix as the critical point of the square of the scalar curvature, like the integral of the Calabi function, and you take the integral over n over the Sasaki manifold. And then they proved that it was equivalent to the fact that the gradient of the scalar curvature is real holomorphic, and this is the way I am using it all the time. But yeah.
Thanks.
Hi, Evelyn, this is Vestislav. I want to complement to the question of Charles. Yes, so when we have a quasi-regular, we need to work with.
I can't hear.
Do you hear now?
Yes.
Okay. So yeah, so the main problem, technical problem to working with quasi-regular quotients is that we need a pluripotential theory, which so far is available in the regular case. However, in the Sasaki-Einstein case, in the Fano case, recently Chi Li developed singular techniques, and indeed he used this approach to derive a general stability result through this method. So in the Fano case, that's done because we work with Dink energy rather than Mabuchi energy. So
I'm sorry, I didn't hear. I can't hear now.
Okay, so I'm saying that Chi Li had a recent work working in a quasi-regular situation. So
yes.
it's possible to say something. Yeah.
Yes. Okay. Yeah. Thank you.
Any other questions? I can't see if anybody has their hand up. If someone has their hand up in the Zoom room and I don't see it, just okay. It doesn't look like anyone's got their hand up. Okay, well, let's thank Evelyn again.
And thank you.